So I want to start out by asking a question, which is really going to set the tone for the way that we view robust qualities in the study of complexity. So let's say that I have a song, okay? It's, I'll make it a Muse song, okay? Newborn, cool. So I have this song, it's called Newborn. I want you to think about how much about that song do I have to change, what the actual notes are, what type of rhythm is in the song, is it an acoustic version, is it instrumental, is it just the vocals? How much do I have to change about that song before it is no longer the original song to where you can't recognize it? And just think about that. There are a lot of nuances to the question, but that's going to get you in the right mindset for thinking about a robust quality. For now, let's talk about the idea of an exact quantity. Exact quantities, well, in the real world, precise quantities are the things that we tend to use in physics to say, that's where we get our authority in physics, honestly. So let's think about how I would use a precise quantity in physics. So let's say I want to know something, and I want to know something in the future based on what I see right now. Okay? We can think about the variables in my world, the things that change in my world, as the things that I can measure, and we can think about them as things that I can't measure. So let me explain what this equation is. This is the equation of universal gravitation. Okay? So this shows me, based on the mass of the objects involved, such as myself and planet Earth, and the distance of these two objects, this shows me how quickly I am going to accelerate towards the Earth. These are all things that I can measure. It turns out that there has to be a constant involved that shows me just how these two numbers relate. And they're just numbers. In physics, we use quantities to predict other quantities, mostly measurables. Now, I can't measure this constant directly. It's impossible. What I have to do to get this constant is take the things that I can measure and the things that I can control, and I change them to see the way that they change the other thing that I can measure, the thing that I can't control. So let's say I have two masses, and I want to see how they relate to the way that they attract each other, based on the values of the masses. This is called the Cavendish Experiment. I would recommend you look it up. It's a great piece of science history, and it's really just a brilliant experiment. But what I would do is I would take these masses and I would vary the value of the r squared, and I would see, okay, how do they attract each other based on that. There's more to it than that. It's much more subtle than that, but the idea is that I'm taking some measurables and I'm changing them, and I'm seeing what happens to this variable. And that helps me determine this constant. Now, the idea of precision has to do with the degree to which I can know this constant. So if I measure this constant right here in Georgia, and then my friend measures the constant over in Arkansas, or it doesn't even have to be Arkansas, it could be here in Georgia as well, there will be fluctuations in the value that I get to some degree. At some point, our answers are going to be different because there are conditions about my environment and my friend's environment that we can't control. So the way that we get around the fact that our answers are different is at some point we just kind of truncate them. So let's say I get, my gravitational acceleration g equal to 9.812. And in terms of modern technology, that's not very precise at all. But my friend gets it to be, and I'll label this G1 and this G2, my friend gets 9.813. 3. We can't agree on this digit. So what we say is that we're just going to leave this digit off, and we can agree on this. That's how we establish the idea that a relation is correct to a certain degree. And the reason this is important is because we can use this relation in other situations. We can reproduce the results and show that it is valid on the moon, Mars, wherever you want to be. So this becomes incredibly useful as kind of a rule that you can use in any situation. It's a guide that you can use no matter where you go. We can make predictions that will help us get to the moon, keep a satellite in orbit, launch projectiles. This is an incredibly useful relation, and our ability to use it relies on how precise we can be. So let's say I want to land on the moon. There's a very specific level of precision that I have to reach in order to know that I'm going to actually get to the moon, as opposed to just missing it and slingshotting off into space. Precision can be a big deal. So precision is kind of the workhorse that allows us to get these relations as this really certain definition of what the universe does. And that drives most of physical science. So now we have to abandon that. We have no idea what the we have no idea what the variables in a complex system are most of the time. So what we need to do is come up with some analogous idea that allows us to make the same types of predictions that we were making in our exact quantity model. So I want you to think about that song again. The robustness of that song is the degree to which I can be certain that I'm going to reproduce that song if I play these notes. So in computer science, this is a way of being certain that you're going to perform the same computation without, mucking it up because your variables changed, maybe a bit flipped and caused the answer to be different. That's a very technical way of saying it, and if you don't understand, once again, ask me in the comments, and I will be happy to explain it. I'm a much better written communicator than I am a verbal communicator. But a robust quality is a quality that I can be certain, to a certain degree, that I'm going to reproduce it under certain conditions. Same idea, you can get reproduction of qualitative results to a certain degree of precision, which precision isn't really the right word because we don't necessarily care exactly what the value of our conditions are, such as like the temperature, the number of particles. Sometimes it is important, the number of particles that you have, but what we really care about is how much error can I have in reproducing these qualitative results. Exclamation point. Because this is our common theme here. We want to be able to predict the world around us, but we need the right tool to do it based on what we're trying to predict. Maybe I want to predict whether or not an ant colony is going to survive. It wouldn't really help me to know exactly how many grains of sand are available for that ant colony to build with, but it would help me to know that I do have all the qualitative requirements for an ant colony: a queen, workers, environment, food, things like that. And other qualitative components would be nice to know as well, such as carrying capacity of the environment, climate fluctuations, rainfall, things like that. These are qualitative things that we don't really care about the precise value of, but we do care about how robust the result is, the ant colony surviving. So we're going to be exploring robust qualities throughout these videos, and it's really important to have a solid understanding of what that is. So, yeah.